Dear ladies and gentlemen, it's my great pleasure to introduce our keynote speaker, Professor Andrey Ustyuzhanin. Andrey was director of AI and machine learning research at Acronis and a visiting research professor at National University of Singapore. His research focuses on designing new machine learning methods and applying them to tough scientific challenges. So, starting from September this year, Andrey is officially a professor of computer science here at Constructor University, and he will share today some of his latest research with us. Please welcome Andrey here on stage.
Yeah, thank you very much. In this talk, I'm going to cover some of the results that we obtained recently with really international collaboration, interdisciplinary collaboration of people coming from NUS, HSE, Yale, NUS College, and so it's a really multifaceted topic related to finding new electrolytes for new generation of batteries. So the main question when we talk about new generation of batteries is how do we store in a green way, in a sustainable way, the energy that is available out of sustainable sources, renewable sources like wind or sun, so which are not available during maybe night or during some extended period. And how can we efficiently do it at scale, right? And of course, battery is one of the answers. And the thing is, there are like two different branches of batteries. So one is traditional, that is based on lithium ion, that are structured in a way that ion travel in a liquid electrolyte. So it's a special solution that are prone to leaking and thermal runaway, so it's not very sustainable. And there are some safety concerns that limits performance and applications of it. And alternatively, you can rely on another kind of electrolytes that are made of solid material, like crystal materials, where ions can easily travel through the crystal lattice. So, and we call it solid-state batteries, and then they effectively allow us to get rid of shortcomings of traditional batteries, of the one that we use every day. So, and just to illustrate what's going on, I mean, what kind of batteries we're looking for. So we look for a crystal that allows some of ions inside the crystal to move freely in the crystal lattice. And it's not usually the case. So usually ions sit in the nodes of crystal lattice and do not move anywhere. Unless heated to a really high temperature. But in some cases, it is possible. So in some cases, very light ions, for example, lithium, which is number 3 in the periodic table. So it can move a little bit. And in some materials, it can move, or it can transverse really high distances. And the question is, can we find specific materials that allow these ions to move more or less freely? So it's really difficult because these materials are rare, and to do it in a proper way, a traditional way. Our way is also proper. So to do it in traditional way, you have to screen large collection of materials, either experimentally or computationally. Now we can rely on computational methods, but it's really computationally expensive because you need not just to model a crystal lattice at particular temperature, at zero temperature state, which means that every atom has fixed position, but we need to model it at higher temperatures. So, and you need to model it during extended period of time, like several hundred of picoseconds. So it takes a lot of resources. And so, as I mentioned, traditional approaches, either experimental or quantum simulations, are expensive and very slow. And it means that discovery of such materials would take years, like 10 years or even more. So what we want to do is to invite AI methods to speed up this process, to speed up this screening that would lead to discovery of such materials. And how can we speed it up? So this is a spoiler. In our case, our method allows to win 3 orders of magnitude in the speed of screening compared to traditional computational approaches. So there are several components that we rely on. So the first one is called machine learning interatomic potentials. It's not our invention. These potentials has been around for some time, but it's essentially learning AI to understand how individual atoms push or pull each other in the crystal structure. So they somehow, without any computation, without any physics computation, allow to find the forces that affect each individual atom. And if we run a system of atoms for long enough using these interatomic potentials, these machine learning models kind of set in place individual atom, and we can rely on the configuration that we get afterwards. So it's kind of AI playing atomic Lego in the right way. And one of the results of applying these interatomic potential to the crystal structure is that there are certain pathways or certain landscape features that we like observe in our everyday reality, like valleys or barriers that some atoms can follow or can block motion of these atoms. And understanding of these landscapes gives a key to understand what is the possible motion of an atom that we need to push from one atomic cell to another atomic cell to make the material electrolytic. So, and the key insight here is that superionic conductors have this energy landscape, whereas the smooth pathways that allow atoms to go from one place to another. So, and the question is, can we, using another AI approach, teach which configurations have these features, these smooth valleys? Then you can do a very simple thing. So imagine you have a volume of the atom with some atom placed in this lattice, like you have here or here. So and imagine you put and this green is a lithium, and you put this green atom at every point, like scanning every possible position, and then measure force that is given by machine learning interatomic potential that does affects this atom. Like, and we do it like scanning cubical volume of unit cell. So we compute it in many places, and then we get kind of this landscape. So it's depicted here by this red thing and this red surface that shows prohibitively large potential areas, like potential barriers that green atom cannot go. And if there are volumes that are not colored in this red color, in this red, that green atom can go through, so it means that it is possible to push the atom from one position to another position, and it will be able to conduct electricity from anode to cathode, or vice versa. So on the right side, you have some examples of atomic structure that has this volume of this potential surface represented by the red color. And on the left, it's Google VO3 model where I try to visualize how this energy surface look like. And this red thing correspond to the barriers that atom cannot go through. So it sits inside, confined in a particular volume in this case. But you see there are some configurations on the right that has pretty large space for atoms to move. So, and how do we scan the variety of atomic material, crystal materials, to recognize such materials that has large space open, that allows lithium atom to move around? So we trained another neural network that takes as input the atomic configuration of atoms and predicts some properties of the volume. So in properties that we took into account was based on geometry analysis. So measuring the size and connectivity of the pathways through the crystal structure, or identifying regions where ion can move with minimal resistance. So it's basically some quantitative assessment of this free space, of free volume. As I mentioned before, we just build this potential energy surface. PES stands for potential energy surface, and we fixed all the atoms besides lithium, and scan this free volume, the volume below with energy below certain threshold, to get these descriptors called free volume and energy barrier. And we tuned these descriptors to perform reasonable results on simulated and experimental data available. And we combine these descriptors to produce a single score that we use to estimate the mobility of atoms. So this is a pipeline that we used in this work. So we started from the training of these models and then generate energy landscape and extract descriptors from these landscapes. Then we run the whole database called Material Project that contains 200,000 different materials through these descriptors and select top performing materials, the top that has highest ionic conductivity property. So and validated the top performers using computational assessment of this motion. So we just switched on the temperature and let the lithium ion run, whatever trajectory they choose. And the longer they run, I mean, the further they run from the initial point, means that they have a higher conductivity. And here is the top table of top ranked predictions. Out of 10, only 2 seem to be are not good having ion conductivity. Some of them have known experimentally measured ionic conductivity already, but in addition to known materials, we found one that has very promising conductivity, but it hasn't been studied yet. So it's lithium hydroborate, and to best our knowledge, nobody tried to study this. And so if you have any friends in chemical lab, so we'd be curious to see if experimentally the conductivity of these materials can be confirmed. So the story is not complete yet, but maybe, so we couldn't find a reasonable people who could help us with this, so maybe you can. So this is just to summarize what we have. We designed the pipeline that is able to give us reasonable properties of electric ionic conductivity, just taking into account atomic structure of materials. And it, out of top AI predictions, 8 materials showed super ionic behavior when we tested them, validated them computationally. And so the speed improvement compared to regular pipeline is 3,000. So that's basically it. With hopefully with help of similar approaches, we can not only search for new batteries, but also like design these batteries as well. So besides finding just the electrolyte that allows to transfer ions, there are other important issues: how to design cathode and anode, and how to make interfaces stable enough. But still, this approach seems to be quite promising in this direction. Okay, so probably the broader lesson is that in this particular example, and in many examples of AI applied research, AI doesn't replace human agency or human expertise, but augments it and allows people to look broadly with bigger context or understand bigger picture. So just to conclude, so if lithium ions can find their expressways, maybe humanity can find its own way to the safer future with better energy capabilities. So to conclude, you can scan the QR code if you want to get in touch and interested in collaboration, letting me know about experimental validation of this lithium hydroborate. So thank you very much for your attention.